With numbers, we know what an inverse is. 2 has the inverse 1/2 because 2 times 1/2 is equal to 1. Matrices work the same way. Multiply a matrix by its inverse and you get the identity matrix, the equivalent of 1 for matrices. This matters because inverses let us solve entire systems of equations in a single step. In this video, I'll show you what matrix inverses are and why they're so useful. Hi, I'm Oliver. I study computer science and make short, accessible videos on the core ideas behind math and computing. Today we'll look at matrix inverses, a key idea that builds directly on what we've learned before about matrices. If you haven't seen my introduction to matrices yet, I recommend starting there first, since we'll be building directly on matrix multiplication in this video. So I want to start off with the identity matrix. So at the beginning of the video I mentioned that the multiplication of a matrix with its inverse equals to the identity matrix. And I'll show you what that is. So the identity matrix is generally written as capital I subscript n, and this means it's an identity matrix of size n. Here you see the identity matrix of size 3. Size 3 means that we have 3 rows and 3 columns. Identity matrix is always square, meaning the number of columns is equal to the number of rows. The defining characteristic of an identity matrix is that all entries are 0 except those on the diagonal. So we can say that as long as the row and column index are the same, so in this case first row, first column, in the second case second row, second column, the entry is always 1. And for every other case, it's 0. Now, we mentioned this analogy with the number 1 at the beginning, that multiplying a number with its inverse gives us 1. And we know from 1 that if we multiply it by any number, we just get that number back again. The same is true for the identity matrix. Multiplying this identity matrix by a compatible vector or matrix just gives us that matrix again. I will demonstrate that quickly. Here we have a matrix multiplication of our identity matrix and the vector 1, 2, 3. We know since that our left-hand side matrix has size 3x3 and our vector on the right side has size 3x1, if we consider it a matrix, that our output will then have the size 3x1 as well. Applying matrix multiplication as we've learned it in the past, we take the first row of the first matrix and multiply it with the first column of our second matrix, the only column. In this case, we do piecewise multiplication, so our 1 is multiplied by this one and added up to the result of multiplying this value times this one, and then adding up to this value multiplied with this one. Since these are zeros, we do not get an output from here, so we would be adding with 0, meaning our result will just be 1 in the first entry. Now with the second row, you can already see a pattern. Since we have 2 zeros here, namely in the first entry and the third entry, these values will not be relevant. So this 1 and this 3 we can neglect because they will not have an impact on this output here. So only this 1 gets multiplied with this 2, so we enter this 2 in our second position. And the same applies for the last row, where the first 2 entries are multiplied with 0, and the last one is multiplied by 1. So 1 times 3, and this will then be the content of the third row. And now you can see that the vector which was originally multiplied by this identity matrix is the same one as the output. The same is true for multiplying matrices with more than one column. So this time we have a 3 times 3 matrix multiplied by a 3 times 2 matrix, so our output will be a 3 times 2 matrix. For our first column, we start with the first column of the second matrix, and then for the first entry again with the first row of the first matrix. You can see again we only take the first entry, meaning this 2 here, since we multiply this row times this column, so we get a 2 here. Then this row times this column, we get a 1. Then third row, this 1 multiplied with this 3. And then once we're moving to the second column here, it means that we're multiplying by the second column on the right-hand matrix. So again, multiplying yields us 4, 6, 5. I did this a bit faster because the pattern is the same anyways. But here you can see that the function of this identity matrix is very similar to a 1 in multiplication. It always yields us the same result. So now that you've seen that the identity matrix acts as multiplication with a 1 for matrices, we can reveal here that this question mark indeed tells us that this result is the identity matrix. So this multiplication with real numbers, its equivalent in matrix multiplication is this one. Now, when we talk about matrix inverses, there's one important consideration, namely that we're talking about square matrices always. There are other types of inverses, like the pseudo-inverse, but we'll not get into this today. So as mentioned, these matrices need to be square, meaning they have size n times n, since our identity matrix is of size n as well, and then our multiplication of n times n matrix times an n times n matrix would give us this same size. Another consideration is that certain matrices do not have inverses. So for example, looking at the matrix 0, 0, 0, 0, there is nothing we can multiply to it. So let's just put some variables in here. There's nothing we can multiply so that it gives us this identity matrix. The reason why is because of this 1 here. It tells us that multiplying this row with this column would have to give us this 1 here. But this would mean that 0 times A plus 0 times C is equal to 1. But we know that these zeros cause the left-hand side to become 0 and the right-hand side stays 1. And then we get this contradiction. So we do not have an inverse for this matrix here. And there are many matrices which do not have inverses. But now, how exactly do we find the inverse of a matrix? So, for example, for our matrix A here, this 2 times 2 matrix, how do we know what the inverse of A is? Now, there are certain methods, but one simple method, which we can specifically use for a 2 times 2 matrix, is to use a formula, namely this formula here, which tells us exactly if we have the entries A, B, C, and D, where these have to go in our matrix and with what we need to multiply this in order to get the inverse. Now this is a really neat solution because we can just plug in values. And if you want to verify that this formula is correct, I suggest that you grab a sheet of paper and you write down A times the inverse of A, and then you plug in these matrices and solve it yourself, and you'll see that the result is our identity matrix of size 2. And you'll also notice that if you try to multiply using the inverse on the left-hand side, you will also get the same result. And this is not always the case where you can just switch around the order of matrices and still get the same result. But for inverses, this is the case. Now there's also a formula for the 3 times 3 matrix case, but it does get a little bit more complex or confusing. I will not show that formula here, but it is important to realize that there isn't a known formula for each size of matrices, at least not one that can solve it in one step. And this makes the computation of inverses less practical. There do, however, exist alternative methods of solving these matrices, ones which would not yield a result in a single step like this formula right here, but which can iteratively, so step by step, create the answer. And one of these examples is Gaussian elimination, specifically a variant of Gaussian elimination called Gauss-Jordan elimination. This method is somewhat more complex, and I may make a video on this in the future, but I wanted to mention it because it is a very relevant and useful method of determining inverses. The reason this method is so relevant is because of this equation which we know from the previous video, ax equals b, which helps us represent linear systems of equations. We can apply this Gaussian elimination method in order to solve for x. So to get the result x equals inverse of a times b. And we can do so in a way which does not require us to use a formula like we've seen up here, and instead make simple operations on this original equation so that we can build our result and easily read out the values of it. So to elaborate real quickly on this change, or rather this solution which I've shown, this actually comes from multiplying with our inverse. So originally we have ax equal to b, and in one step we multiply both sides by the inverse of a, giving us the inverse of a times x equals the inverse of a times b. And as we've seen before, the order we multiply this inverse in does not make a difference. So we straight up get our result x equals the inverse of a times b. So I've mentioned the Gaussian elimination method of solving this or getting our x. But if we know the inverse of a, we do not need to do this, but we can just do this simple matrix multiplication and we immediately know our result. And this result then being the solution for our linear equations. The benefit of using Gaussian elimination is that it doesn't just work for square matrices, and there does not have to exist an inverse. To learn more about Gaussian elimination, check out my video on it, or watch this other video instead. If you enjoyed this overview, subscribe to stay up to date with new videos, and leave a comment with what you would like to learn about more. And as always, thanks for watching.